Hey, how are you? And welcome to the week number 3 material, and it's going to be mainly about the casting processes. So through this slide, I'm going to take you through the parts of the material that's already been available for you on the canvas, but I'm going to actually going to cover here the notes that's already been supplied to you as well. So I'll go with the first part of this session, which is going to be about the overview of the casting technology, some heating and the pouring knowledge, and then we're going to talk about the solidification and the cooling. I left part of the material like the shrinkage to be discussed in another video. So we start with solidification and processes in general. All the manufacturing will start by getting a material, and this material needs to be melted, and then we are going to put in a mold that have the same shape of the part that we are intended to have, or it's going to be something like the initial shape of the part you would like to have, and then we leave it to cool down or solidify. So starting work material is going to be either a liquid or is in a highly plastic condition. The part is going to be created through the solidification of the material. So when we say it's going to be either liquid or it's going to be highly plastic condition, because there are different types of the casting processes. It doesn't have to be highly liquid because this sometimes is going to be uncontrolled. So we may just have it as a flexible enough in order to take the shape of the part of the cavity we have in the mold. The solidification processes can be classified according to the engineering material processed. So we can have them for the metals, we can have them for the ceramic, specifically the glasses, and that's when we mainly going to have it as the highly plastic material, not as a fully liquid material. Also for the polymers and the polymers matrix composites, or what we know as the PMC. So this is a classification of the solidification processes. So you can see that we can have for the casting of the metals, which can be classified into expandable mold and the permanent mold for the glass working and the processing of the polymers and the PMC, sorry. So today we're only going to focus on the first part, which is going to be the casting of the metals. So what are the advantages of the casting? Complex parts geometries can be achieved. Can create both external and internal shapes. Some of the casting can be to the net shape and other can be to the near net shape. Well, the net shape is going to be that the part is going to be used directly, and that's what we have in the die casting processes. The near net shape, that means is going to require to put a certain amount of the machining in order to get the final shape. Also, very large parts are possible. Just remember that we have something as big as the crankshaft or the engine block of a ship. Just imagine how big it is. It's all going to be done by the casting. And also some casting methods are going to be suited for the massive production. Still have disadvantages, which are going to be the limitations on the mechanical properties for the casted part, poor dimensional accuracy and surface finishing for some processes, mainly for the sand casting. Also, some safety hazards to the worker due to the hot molten metals. Definitely the environmental problems due to the fume and to the smoke generated from the coal we are going to burn in order to do the melting of the metals. A brief overview of the casting technology. The casting usually going to be performed in a foundry. The foundry is the workshop that they do the casting in it. It's a factory equipped for making the molds, melting and handling the molten metals, performing the casting processes, and cleaning the finished casting. Workers who perform the casting is usually going to be called the foundry man. The mold in the casting, why we need the mold in the casting and what will be the purpose of the mold in the casting. First is going to contain the cavity whose the geometry determines the part shape. The actual size and the shape of the cavity must be slightly enlarged because the part is going to be shrink. So we're going to slightly enlarge the mold cavity. So when it's going to be cooling down after the solidification, it's going to take almost the dimension of the part we would like to have. The molds are made in a variety of the materials, including the sand. It can be a plaster, it can be ceramic, and can be even metal. They can be classified into two main types, the open mold and the closed mold. So the open mold was the oldest type. Maybe I explained that in different sessions when I said that simply you can make a cavity on the floor, a groove on the floor, then you fill it with the metal and you're going to have the shape of the part you would like to have. That's the open mold. The top is going to be exposed to the air. And the other type, which is the closed mold, the cavity is going to be inside the mold. Only the pouring cup and the vent actually is going to be uh, open to the space, to the outside. The shape of the mold, the closed one, is going to be a very high possible question in the quiz. The two categories of the casting processes, we have two types. The first one is going to be the expandable mold processes. That means our mold is going to be sacrificed in order to remove the part out. Usually can achieve more complex shapes. Also, the production rate often is going to be limited by the time to make the mold rather than the casting itself. The other type is the permanent mold processes, where the mold is going to be made of the metals that can be used to make many castings. Higher production rates and the geometry are going to be limited by the need to open the mold. And that's what we have in the case of the die casting. So briefly about the sand casting mold. That's the same photo that we saw earlier. We see that simply the mold consists of two halves. The cup, which is going to be the upper half of the mold, and the drag is going to be the bottom one. The mold half contained in a box, and this box is going to be called the flask. The two halves separated by a parting line in between them, the dashed line we can see in the photo. The forming of the mold cavity in the sand casting. We are going to use the core in the mold cavity. So the mold cavity is formed by packing sands around the pattern, which is going to has the shape of the part. When the pattern is going to be removed, the remaining cavity of the packed sands has the desired shape of the cast part. The pattern is usually going to be oversized because we said we're going to consider the reduction in this volume due to the shrinkage later. The sand for the mold is moist and contain a binder to maintain the shape. Otherwise, if it's going to be dry sand, definitely is going to be collapsed immediately. So how are we going to use the core in the mold cavity? The mold cavity provides the external surface, while the internal surfaces is going to be determined by the core. In the sand casting, the cores are generally made of sand. We're going to show some samples in the lab later. So these are examples for the pattern. Okay, the pattern can be made of wood, can be made of plastic, and can be made even out of metal. The internal cavity inside the pattern, where we made the cavity of the mold, we're going to put the core in order to have the cavities like what we have in the left photo. You can see that we have cavities inside. These cavities are going to be made by putting the core inside the cavity generated by the pattern, the wooden part on the left, on the right, sorry. So we have the cavity inside. We need to reach to reach the metal to inside the cavity. To have that, we should have a gating system, which is a channel through which the molten metal will flows into the cavity from the outside of the mold. Consists of the downspur through which the metal enters the runner, leading to the main cavity. So downspurs is the vertical channel. The runner is the horizontal one. We have also the pouring cup, which often going to be used to minimize the splash and the turbulences as the metal going to be flows into the downspur. The riser is a reservoir in the mold, which is a source of the liquid metal compensate for the shrinkage of the part during the solidification. The riser must be designed to freeze after the main casting in order to satisfy this function. So let me explain that to you. When we're going to fill the cavity with the molten metal, and then within the time, we start to have the cooling of this molten metal. So it starts to shrink. When it starts to shrink, we are going to have some cavity need to be refilled once again with the molten metal. So to achieve that, we are going to have reservoir in the mold. This reservoir is going to be containing a molten metal that will remain molten even when the part starts to solidify. So when it's going to have the molten metal, it's going to be filling the cavities that caused by the shrinking. Then we are going to avoid having the shrinking of the part. Now heating the metal. We know that we have a melting temperature for every metal. So the heating of the metal to molten the temperature sufficient for the casting. The heat required is going to be the sum of, first, the heat to raise the temperature to the melting point. But that's not going to be enough to melt the metal. So we need to add an extra heat, which is called the heat of fusion, that converts it from solid state to liquid state. And then we're going to add more heat to raise the molten metal to the desired temperature for the pouring, which is going to be a temperature higher than the melting temperature. The pouring temperature is the temperature that causes the metal to be more soluble in order to be poured and fill the cavities before we're going to have any pre-freezing for it. So for the pouring of the molten metal, for this step to be successful, the metal must be flowed into all the regions of the mold, and most importantly, the main cavity before it's going to be solidifying. The factors that determine the success of the pouring is going to be first, what is the pouring temperature and what is the pouring rate, and the possibility of having the turbulences which draw back the flow inside the channels. So you can see here the transformation of the molten metal back into a solid state. So just get it cool down from the outside first to the center at the end. Mainly because the heat is going to be transferred from the outside of the cavity to the mold sand, then to the outside, while the core is going to contain having a higher temperature. By the way, these vertical cylinder are the risers that we talked about. Okay, so solidification of the metal is transformation of the molten metal back into solid state. Solidification differs depending on whether the metal is going to be pure elements or an alloy. I think we explained this one earlier. If I'm going to have a pure element, we're going to have one melting point, one solidification point. If we're going to have an alloy, we're going to have two different melting points and two different solidification temperatures. So the cooling curve for the pure metal. The pure metal solidify at a constant temperature, which is equal to its freezing point, which is the same as the melting point. So you can see in this diagram, in the y-axis we have the temperature, while in the x-axis we have the time. So when you heat up the temperature, we're going to move from the right to the left. So we increase temperature, we're going to reach the melting point. We add the heat of fusion, we're going to change it to the liquid uh, uh, state. Then we're going to add further temperature, further heat to reach the pouring temperature, which is the highest. Okay, now we pour the metal. We're going to go back from the left to the right. So we're going to drop the temperature from the pouring temperature to the freezing point, which is the same as the melting point. We keep losing the heat, which is the local solidification time, until we're going to reach the freezing point, which is going to have the freezing completed. Then we're going to cool down the metal and we're going to have shrinkage. Now, what does this call? Let's see the solidification for the pure metal first. In the case of the pure metal, due to the chilling action of the mold wall, because, well, even the mold wall is going to have 100 degrees temperature, but remember that the minimum melting temperature again to use, for example, is going to be 400 degree. So the difference of 300 degree or more is going to cause a chilling at the beginning. So that's why we're going to have the thin skin of the solid metals is going to be formed at the interface immediately after the pouring of the molten metal in the mold. The skin thickness is going to be increases to form the shell around the molten metal as solidification progress. So you can see the small granules in this photo. This is due to the chilling we had for the molten metal. The rate of the freezing will depend on the heat transfer out of the mold, as well as the thermal properties of the metal we are pouring. The characteristic grain structure in the casting of the pure metal shown randomly oriented grains of the small size near the mold wall, while it's going to have a large columnous grains oriented toward the center of the casting in the middle. Now, in the case of the alloy, we say we're going to have different melting temperature. So now you can see the photo to the left and the photo to the right. I think that you remember the photo on the left because we saw it earlier, which is going to be what will be the case of the solidius and liquidius and the mixtures in the middle. So how this will be explained as the freezing temperatures. So we are going to move first for the figure B from the right to the left. We add the temperature, we add the heat. So again, to reach the melting temperature of the first metal, it starts to melt, while the other one will remain as a solid. So again, to have mixtures of a solidius and liquidius in the middle, until we're going to reach the temperature for melting the second metal, and thus both going to be liquid. We add more heat, we're going to reach the pouring temperature. So we're going to pour the metal inside the mold. The curve will go from the left to the right. So we are at the pouring temperature, liquid will cooling, we're going to reach the freezing temperature, which is the melting temperature of the higher melting metal. And then we're going to keep cooling down. We're going to still have the mixture of the salt and the liquid until we're going to reach the melting temperature of the second metal, which have the lower melting temperature, and then both going to be solidified. And then we are going to keep cooling down. So how that will look like as a grain. So in the alloys, once again, we're going to have the small grains around the wall because we had the chilling thing. Then in the middle, we're going to have the mixture of the liquid and the salt, as we mentioned earlier. We're going to have the columns first, then we're going to have the small grains in the middle again, which is going to be the remain of the molten metal that's going to be solidified at higher rate later. So if we're going to cut it down, that's what we're going to see. Now, the solidification time, which is something very important. Usually, we don't want to keep the things working for solidification after a long time. At the same time, we don't want it to pre-solidify. So there's a time to be calculated, and this will be a part of your design as an engineer. So the total solidification time, or the TTS, is the time required for the casting to solidify after the pouring. The solidification time depends on the size and the shape of the casting by a relationship known as the Chevrinian rule. Remember something that the larger size and the more complicated shape is going to take longer time to cool down. So the Chernow's equation tells us that the time for the solidification is equal to the Cm multiplied by the V divided by the A up to power n. So let's see what are these terms. First, the V is the volume, A is the area. That's the concept. And the Cm and the Cs and the Cm and the N are mainly the mold constant for the Cm, and n is going to be the exponents of the typical value, which is equal to 2. V is the volume, and the A is the surface area. The equation will tell me is that the bigger the volume is, the longer time for the solidification. The larger the area is, the faster time for the solidification. Because in the surface area larger, we're going to have a higher rate of cooling. So the mold constant Cm will depend on the mold material, the through properties of the casting metal, and the pouring temperature relative to the melting point. We had an example on the tutorial which using the Chevrionov equation. The value of the Cm for given casting operation can be based on the experimental data from a previous operations carried out using the same mold material, metal, and the pouring temperature, even though that the shape of the part may be quite different. So this is the end of the part 1. Thank you very much, and we're going to continue with the part 2 next.